Okay, we are going to continue our discussion about speaking mathematically, getting the terms and the symbols that we're going to be using throughout the rest of the semester, getting those formalized and defined and understood, hopefully. Okay, so today, section 2, we are going to be talking about the language of sets. Now, the use of the word set in mathematical circles was introduced in 1879 by Georg Cantor. Basically, you can think of it intuitively as a collection of elements. Come on. There we go. So we can see. Okay, but formally, use the notation X with the stylized E. It indicates that X is an element of E, of X is an element of S. The notation with a line through it means X is not an element of S. Use set roster notation by writing its elements between curly braces, like 1, 2, 3 in the curly braces. This is very similar to how you define an array in C++ if you know all the elements in advance and you want to hard code that into your program. With large sets, you can use an ellipsis to imply a sequence, such as 1, 2, 3, ... 100 means 1 to 100 all the way through. Or the ellipsis at the end of the set to indicate that it goes on infinitely. The axiom of extension says that a set is completely determined by what its elements are, not the order in which they are listed, or the fact that some elements may be duplicated. Okay, this is where it's different from an array in C++. So, let A be the set 1, 2, 3, and B be the set 3, 1, 2, and C be 1, 1, 2, 3, 3, 3. They are all the same set. They are different ways of expressing the same set. Now, how about the set of with the element 0 equaling 0? Is that true? No, it's not true. Because 1 is a set, 1 is an integer. They're two different objects. It's kind of like, to use the C++ analogy, an array with a single element is a different type of object than an integer. They are handled differently. They are different objects. Now, how many elements are in the set 1, comma, internal set 1? How many elements are in that set? The outer set? 2 elements. The first element is the number 1. The second element is another set with the element of number 1, the number 1. So you can have sets within sets. Kind of like you can have arrays within arrays in C++ to make multidimensional arrays. Same concept. Okay, for each non-negative integer n, let U sub n equal n, comma, minus n. What is U sub 1? The set of 1 and minus 1. Okay? U sub 2, 2 and minus 2. Okay? U sub 0, 0 and minus 0, which is also equal to 0 and 0, which is also equal to just 0. The set with a single element of 0. Because duplication is allowed for equality. So we covered those two already. So in D there, and you can see where 0 and minus 0 are elements of the is a valid set. 0 and 0 is a valid set because 0 and minus 0 are the same. They're equal, which equals the set with a single element with the number 0. Now there are certain sets that are so frequently referred to, they have their own special names and symbols. Are real numbers. So 3.14159265, real number, that's in R. Z is the set of integers, whole numbers. And Q, don't see as often, but it is the set of all rational numbers. Remember the Q as being a quotient between two integers. So those three are fairly commonly used. The addition of a superscript, plus or minus, or the words or the letters non-neg, indicate that only the positive, negative, or non-negative elements of the set are to be included. Thus, R plus would indicate all positive real numbers. Z non-neg would be non-negative integers. 0, 1, 2, 3, 4, so on. I have seen this. Some authors refer to non-negative numbers as the set of natural numbers, or N. So natural numbers is the set that is used for indexing arrays in C++. They start with the index starts with 0 and goes up to the limit of the size of the array. The set of real numbers is usually pictured as a set of all points on a line. 0 being in the middle, called the origin. We used number lines in we stopped. When did we stop using number lines? About 5th or 6th grade for counting and that sort of thing. So it's just the distance from the origin. To the right it's positive, to the left it's negative. Yeah, we're all familiar with number lines, and unless math education has dramatically changed since I was young. But there you go. Real numbers is therefore divided into 3 parts. Positive real numbers, negative real numbers, and the number 0. 0 is neither positive or negative, nor negative. Let's see here. Now, set builder notation is a way of constructing a set where S is the set. Let P of X be a property that the elements of S may or may not satisfy. We can define the new set as the set of all elements in S such that P of X is true. Note this as follows. Curly brace, X is an element of S, bar, pronounced such that P of X is true. Given that R denotes the set of all real numbers, S and Z is the set of all integers, and Z plus is the set of all positive integers, what would these sets be? Well, A would be all numbers between but not including -2 and 5. So on a number line, you'd have a hole on 5 and a hole on 2, but a line connecting the two. -2. And B, with X being an element of Z, all integers, it would be the integers between -2 and 5, but not including -2 and 5. So it would be the set of -1, 0, 1, 2, 3, and 4. I see a look of confusion. To be in the set, it has to the number has to satisfy both conditions. The number has to be an element of Z, all integers, and it has to be greater than -2 and less than 5. So it has to be an integer, so -1, 0, 1, 2, 3, and 4. All real numbers between them. And with C, the first condition is X is an element of positive integers. So it would be the integers between positive integers between -2 and 5. Yep. 1, 2, 3, and 4. Yeah. So it's just a way of describing the set. I'm sorry? 0 is not a positive integer. So it would not be in the set described in C. Positive integers start at 1. Natural numbers start at 0. So, slight difference there. Okay. And we went through this already. The number line with the hole on 2 and the hole -2 and the hole on 5, and the line connecting the two is the result. And we went through the B and C. Now, subsets. A basic relation between sets is that of the subset. If A and B are sets, then A is called a subset of B, written with this symbol, if and only if every element of A is also an element of B. So, that means for every element X, if X is an element of A, then X is an element of B. The phrase is contained in or contains are other ways of saying the same thing. A is a subset of B. Okay. It follows also from the definition that for a set A not to be a subset of B, means that there is at least one element of A that is not an element of B. So that means what they have here symbolically with this symbol here. There's at least one element, X, such that X is an element of A and X is not an element of B. Now there's also what's called the proper subset. A is a proper subset of B if and only if every element of A is in B, but there's at least one element of B that is not in A. So they can't be equal. I haven't seen this in the book yet, but I seem to remember this from some math class at the that I've taken before. Oops. That is the symbol for a proper subset, right? Okay. So if that is the symbol used, then there is some element of B that is not in A. Okay? Whereas think of this as like the greater than or equal sign. A is a proper subset or equal to B. So A and B could be the same. You see the slight difference in symbols? I've gone through these slides and I haven't seen them use this symbol at any point yet. But it's good to know that that means a proper subset, so that there is an element of B that is not in A. All right. So let A be positive integers. Let B be the elements of positive integers, or be the integers from 0 to 100 inclusive. And C be the numbers 100, 200, 300, 400, and 500. Is B a subset of A? No, it's not. It's not. It's not a subset or a proper subset, because A is positive integers. B includes 0, which is not a positive integer. Okay, so that is false. C is a proper subset of A. Is that true? Proper subset, not of A, not B, of A. Then yes, it is true that C is a proper subset of A. Do C and B have at least one common element? Yes, the number 100. Is C a subset of B? No, because 200, 300, 400, and 500 are not in B. Now, is C a subset of C? Yes, a set is a subset of itself. So we went through all these. All right. Now, which of these statements are true? 2 is an element of the set containing 1, 2, and 3. Yes, it is an element. Now, is the set containing the element 2 an element of the set of 1, 2, and 3? No, because it is a set, and the set on the right does not contain any sets. Is the number 2 a subset of the set 1, 2, 3? No, because it's not a set. It's just a number. It's not a set. A subset has to be it has to be a set. It shows the relationship between two sets, not a set and a number. Okay. Is D, the set with the number 2 in it, is that a subset of the set of 1, 2, and 3? Yes, because the 2 is a set. It can be a subset of the set on the right. Is the set containing the number 2 a subset of the set containing the set of containing the number 1 and the set containing the number 2? No. More to the point, F is true because a set with the number 2 in it is an element of the set on the right. Yes. Yeah, the stylized E means it's an element of the set on the right. The object on the left is an element of the set. I'm sorry? As we'll look at in a little bit, if the element evaluates to be the same, yes. So, as an example, let's say that is true because the square root of 9 evaluates to 3, and 3, it's equivalent. So 3 is an element of that set. So, yeah, it has to match up in some way for it to be an element. Hmm? 2 is a subset. The number, yeah, that is true. Yeah, because 2 is a set. The 2 on the left is in a set braces, and it's a subset of the element, the set on the right. So yes, D is true. So A, D, and F are true. A, D, and F. The others are false. Okay. Now Cartesian products. This is where you get to write a lot. And it's a little bit, the formal definition they give here is kind of confusing, but given elements A and B, the symbol open parentheses A comma B close parentheses denotes an ordered pair consists of A and B together with the specification that A is the first element of the pair and B is the second element. The ordered pairs A and B and C comma D are equal if and only if A equals C and B equals D. Symbolically, if A equals C and B equals D means the ordered pairs are the same. So order does matter. This is more like the array that you see in C++. Order matters, duplication matters. So this is a particular type of set. So is 1 comma 2 equal to 2 comma 1? No, they're two different. In C++, they'd be two different arrays. They would not be equivalent. Okay, and this is where I was showed a few slides back. Is 3 comma 5 over 10 equal to square root of 9 comma 1/2? Yes, because the elements evaluate to be the same value. What is the first element of 1 comma 1? Yeah, it's kind of a gimme. I'm not sure why they put that in there, but it's either way you're right, whether you're naming this first or the second element. But so no, by definition of equality of ordered pairs on the first one. Yes, by the definition of equality of ordered pairs. And then the first and second elements are both 1. The notation for an ordered n tuple generalizes the notation for an ordered pair to a set with any finite number of elements. It also takes both order and multiplicity into account. I won't go through the formal definition. It's kind of wordy and all that sort of stuff. But basically, if element 1 equals element 2, element 1 equals element 1 in the two sets, in the two pair tuples, element 2 and element 2 are equal in the two tuples, and so on and so forth, then the tuples are equal. So a tuple with 2 elements is a pair, ordered pair. A tuple with 3 elements is an ordered triple. Otherwise, it's just like a 4 tuple, 5 tuple, 238 tuple, whatever. So is 1, 2, 3, 4 equal to 1, 2, 4, 3? No. But 3, negative 2 squared, 1/2 does equal square root of 9, 4, 3 over 6, because the elements evaluate to be the same value. So, okay, now this, I was mistaken. This is where it can get a little confusing. Given sets A1, A2, A3, so forth to AN, the Cartesian product of A1, A2 to AN, denoted by the X symbol between each set, is the set of all ordered n tuples equal to the number of sets, and n is the same, so it's the number of sets is how many tuples there are, how many the numbers there are in the tuple, where A1 is an element of set A1, A2 is an element of set A2, so on and so forth. In particular, A1 Cartesian product with A2 is all ordered pairs where A1 is an element of set A1 and A2 is an element of set A2. That is the Cartesian product of A1 and A2. So, find Cartesian product of A to B. What would the result be doing a Cartesian product? All combinations of elements from A and elements from B. No, it would be x comma 1, x comma 2, x comma 3. Exactly. Exactly. Y comma 3. Okay, what do you notice about the number of elements it has? Yes, it is the number of elements in A times the number of elements in B, so 6. So now the commutative property does not work for Cartesian products. It yields a different result. So don't use your algebra manipulation here. So BA would be 1 comma x, 1 comma y, 2 comma x, 2 comma y, 3 comma x, 3 comma y. Same number of elements, but different ordered pairs than the first one. The ordered pairs are the order of the elements are reversed. So the commutative property of algebra does not apply to Cartesian products. Don't try it. It'll mess you up. Okay, AA. Let's just do that one out loud and instead of writing it all out. But that would be XX, XY, YX, YY. There you go. See, the explanation in the formal definition made it sound a little bit confusing, but once you get the concept, it's like, oh, okay, it's just all combinations. It's all combinations. And we covered how many elements are in the Cartesian products. I'm going to leave E for for a couple of slides from now, but A, Cartesian product B, Cartesian product C. Now, in the first that first definition, it means a ordered tuple with the number of elements equal to the number of sets in the Cartesian product. So it would be ordered triples, would be the result here. Okay? Now, you would have, it still applies, all combinations of elements of A, B, and C. So how many elements would it have? 12, yes. 2 times 3 times 2. Now finally, let R denote the set of all real numbers. Describe R, the Cartesian product of R and R. What does that give you? Not a new concept, you're just relating it to something old. Cartesian plane, a graph. X and Y are real numbers, ordered pairs. So it's a Cartesian plane. The set of all real numbers defines a plane where X and Y are the coordinates on that plane. All combinations of X and Y. So yeah, we went through these already. Now the Cartesian product of A and B is a set, so it may be used as one of the sets making up another Cartesian product. So, oops, let me get rid of my notes. There we go. So you do make all the elements, make the set of the Cartesian product of A and B. That yields these ordered pairs. And then do the Cartesian product with that set with C. Yields the ordered pair as ordered paired from the Cartesian product of A and B as the first element, and then the elements from C in the second element. So the associative property does not work from algebra with Cartesian products. Don't use it. Yields bad results or unexpected results. So yeah. Yes.
And that gives us x, 1, x, 2, x, 3, y, 1.
Mm-hmm.
And why do we continue to do like x, 1?
Because that this x comma 1 is associated with A. This x comma 1 is associated with B. Different elements in C. So it is duplicated in a different ordered pair. So likewise, x2 comma A and x2 comma B. They are different ordered pairs. Nesting is allowed of ordered pairs. All right. Let's see here. We went through this one already. It's ordered triples for a Cartesian product of A, B, and C, but not the same as A and B Cartesian product with C. So they are different. This is ordered triples. The previous slide, those are ordered pairs. So they are different. All right. And we went through that. And we also talked about the R Cartesian product with R is X and Y, and that's the horizontal and vertical axes of the Cartesian plane. Cartesian graph. Okay. Another notation which is important in both math and computer science denotes objects called strings. Let n be a positive integer. Given a finite set A, a string of length n over A is an ordered n-tuple of elements of A written without parentheses or commas. The elements of A are called characters of the string. The null string over A is defined to be the string with no characters. It is often denoted by the lambda symbol and is said to have a length of 0. Personally, I've never seen anybody use lambda to refer to a 0 length string, but whatever. I didn't write the book, so could be wrong. But if A equals if the set A is equal to 0 and 1, then a string over A is called a bit string. So that's what computers read. Bit strings. They only understand ones and zeros. Pretty simple machines. But so let A equal the set A and B with A and B in it. List all strings of length 3 over A that have at least 2 characters that are the same. AAB, ABA, BAA, so on and so forth. Those are all the possible strings given the set of characters used, given in the set description of A. Now, it is important to distinguish between different kinds of data structures and to respect the notations that are used for them. Similarly, in mathematics, it is important to distinguish among these different things because all of them are different objects. They are different objects. The first one is a set with A, B, and C in it. The second one is a set with a set of A and B and the element C in it. Ordered triple. Ordered pair with an ordered pair as an element. And a string. All different objects. So, like I said on Tuesday, this is mathematically formalizing common sense. It is being formal about what you're representing. You may intuitively know what all these things are, but you have to, when dealing with them mathematically, you have to be specific and precise about the notation and terminology. Okay, that's it for that first section. That section. We'll go to, let's see, which one is it? I don't know. Okay, go to the next section. Any questions so far on sets before we dive into the next one, into the next section? Okay. This is going to be the language of relations and functions. Okay. This is where the book gets a little confusing because it uses the relation R, which we already use for real numbers, but it's italicized to indicate that it is a relation from A to B, is a subset of the Cartesian product of A and B, given an ordered pair X and Y in a cross product of A and B. X is related to Y by R, written X, R, Y, if and only if X, comma, the ordered pair X and Y is in R. Set A is called the domain. Set B is called the codomain. So R is a set. It's a subset of the Cartesian product of the two sets, the domain and codomain. X is related to Y if the ordered pair XY is in set R. Okay? So, let A be 1 and 2, B be 1, 2, and 3. Define a relationship from A to B as follows. Given any X and Y that's an element of the cross product of A and B, X comma Y is an element of R means that X minus Y divided by 2 is an integer. State the ordered pairs in AXB and which are in R. We'll do that on the next slide. B as well. What are the domain and codomain of R? A is the domain, B is the codomain. So we look at, to determine R, the elements of that are in R, we do the Cartesian product of A and B to yield those these combinations, and then test each one to see if it is an element, if it satisfies the equation that defines the relationship R. So 1, 1 is an integer, so it's an element of R. 1, 2 does not. 1, 3 does. 2, 1 does not. 2, 2 does, but 2, 3 does not. Therefore, R is the set containing the ordered pairs 1, 1, 1, 3, and 2, 2. So you can easily solve B. Yes, 1, R, 3, because 1, 3 is an element of R. 2, R3 is not, because it is not an element. And 2 is related to 2 because 2, 2 is an element of R. How about another relationship where from R to R, real numbers this time, not the relationship. See how these math books can get confusing that way? This is not italicized, so it means the set of real numbers. For any X and Y that's an element of the cross product of real numbers to real numbers, it's an element of C means that X squared plus Y squared equals 1. Okay? What are the domain and codomain of C? The real numbers. Now, anybody recognize the graph? Recognize this equation? Sit down. All right. Does anybody recognize this equation? What kind of circle? Unit circle, yes, from trigonometry. So, yeah. So, goes through and goes through these various examples and shows that which ones are elements of C and which are not. And there's the graph of it. The unit circle. Yeah. Now, one way to represent a relation is using an arrow diagram. Suppose R is a relation from set A to set B. The arrow diagram for R is obtained by representing A points in one region and elements of B as points in another region. And then for every X and Y in A and B, draw an arrow to X and Y if and only if it is related to, if X is related to Y by R. So, say your relation is, your sets are 1, 2, and 3, and 1, 3, and 5. If it's an element of the relation S, means that X is less than Y. And T, the relation T is represented by these ordered pairs. So this, if X is less than Y, draw an arrow from the number to, from the X number to the Y number. So 1 is less than 3, 1 is less than 5, draw 2 arrows. 2 is less than 3, 2 is less than 5, draw 2 arrows. 3 is less than 5, draw 1 arrow. Now T was given by the ordered pairs, so you just go from the 2 ordered pairs, 2, 1, and 2, 5. So you can have multiple arrows coming out of one element and multiple arrows going into one element. Now a function is a particular kind of relation. A function f from set A to B is a relation with domain A and codomain B that satisfies the 2 following properties. For every element X in A, there is an element in Y in B such that X, the ordered pair XY is an element of F. So there has to be an element in B for each element of A. For all elements X in A and Y and Z in B, if XY is an element of X or of F and XZ is an element of F, then Y equals Z. So only one element can be for each, one element in B for each element in A. So by this definition, the square root is not a function, because for all positive real numbers, the square root of a number is both positive and negative. It has 2 results. So the square root of 4 is 2 and negative 2. It's not a function. So if you're dealing with square roots, and I've run into problems with this, if you don't specifically indicate positive or negative square root, it can cause ambiguity and problems in your calculations. But the positive square root, that's a function. The negative square root is also a function. For every element of A, the first element for every element of A is the first element of a ordered pair of F, and no two distinct ordered pairs of F have the same first element. Okay? And it's denoted by F parentheses X, or read F of X as a function. Now let A be equal to 2, 4, and 6, and B equal to 1, 3, and 5. Which of the relations R, S, and T defined below are functions from A to B? R is denoted with a set of ordered pairs. B is denoted with an equation, and T is denoted with a arrow diagram. We'll look at A and B in just a minute, but looking at T, does T look like a function? I see some shaking heads, I see some nodding heads. What's the definition? All elements of A have to have an element in B, associated with an element in B. That's the case with T. And for each element in A, there's only one element in B that it's associated with. That is also the case. So T is a function.
So it doesn't have to hold the element.
No. Like the square root function. It is a function. The positive square root is a function, but the ordered pair 9, 2 is not. 9 does not associate with 2. That sort of thing. And it's not all pairs have to, not everything has to pair up. There's no negative numbers in the result of the positive square root. It's only in the first quadrant of the graph, if you think about it. So negative numbers are not associated in that function. Which of the relations are defined as functions? Are functions. Which of them are functions? So, looking at the definition of a function, this element is associated with the number 5, right? This element is associated with the number 1. Six is associated with number 1 as well. So all the elements of, going back to the definition, every element of A is the first element of an ordered pair. You can't have an element in A that doesn't have a corresponding value in B. Okay? So all the elements in A are associated with a value in B. Right? Yeah, this is let's just look at, let's do A, B. Okay. equals 2, 1, 2, 3, 2, 5, 4, 1, 4, 3, 4, 5, 6, 1, 6, 3, 6, 5. Okay, you got that. Okay, so a function is a subset of, I'm sorry, let me rephrase. A relation is a subset of this, right? And in this case, the subset is 2, 5, 4, 1, and 6, 1. So these are out. Right? You see how those relations, this is X, this is Y. These are all the elements of X, these are all the elements of Y. So when you're looking at whether or not that defines that's what the come on. That's R or T. I'm sorry. That's T as defined by the arrow diagram. That's the relation. Now, is it a function? A relation, a function is a special kind of function, relation, right? So for X is 2, 4, and 6. There is an ordered pair that contains 2, 4, and 6. So that's condition number 1 for a function. The second condition for a function is for each element of X, there's only one ordered pair that has that value as the first element. So there's only one ordered pair with the number 2 in it as the first element. There's only one ordered pair with the number 4 as the first element. And there's only one ordered pair with the 6 as the first element. So yes, T is a function. Got it? Uh-huh.
In other words, so if two objects are in a function,
Exactly. Yeah, what you say, if 2 was pointing like to 2, 3 and to 2, 5, that would not be a function. Think of the functions that you write in C++. When you give it an input, it only has one output. It doesn't change. You give it the same input, give it the same input, it'll have the same output every time. Sometimes the output is void, but that's neither here nor there. Okay. So let's look at questions A. Look at question A. 2, 4, and 6. Well, you got a one with 2, you got 4, and you got 6. So it satisfies the first condition of being a function. But the problem is you have two distinct, these are equal, but these are not equal. So R is not a function. It is a relation, but it is not a function. And we'll look at B on the next slide. Let's see. Oh, okay. Here we go. S is not a function because it does not satisfy the first property of a function. It is not true that every element of A is the first element of an ordered pair in S. For example, 6 is an element of A, but there is no Y in B such that Y equals 7 because of the equation. 6 plus 1, or X plus 1. Y equals X plus 1. You can also see this graphically by drawing the arrow diagram for S. See, there's no arrow going from 6 to any element in B. So it is not a function. If you were to write a function in C++ that did not give a result, did not return a value of some kind through all code paths, you would get a compilation error. It would not compile, right? So a function has to have an output for each input. Okay. Let's see here. We went over T. Okay. Now, sets of strings. Let A equal the set A equal to the elements A and B. And let S be the set of all strings over A. Define a relation L from S to non-negative Z as follows. For every string S in the set of S, and for every non-negative integer n, S comma n is an element of L, means that the length of S is n. Observe that L is a function because every string in S has one and only one length. It could be 0 length, it could be 1, 2, whatever. But every string has a length, so it is a function. And it has only one length. So L A B A A B A would be 6. L of B B B would be 3. Now define a relation C from S to S as follows. For all strings S and T in S, S comma T is an element of C, means that T equals AS, where AS is the string obtained by appending A on the left of the characters in S. C is called the concatenation function. Basically, what that does is you give it a string S and it adds an a to it, yielding t. So C is a function because every string in S consists entirely of A's and B's, and adding an additional A on the left creates a new string that also consists of A's and B's, and thus is also in S. So the concatenation function just adds an A. It takes this and adds the A. Takes this, adds the A. So it is a function, a concatenation function. Now, another way to look at the functions is a machine or a black box. Suppose f is a function from x to y, and an input of x of x. Duplicating letters is like, okay. Input of x to, of the set x is given. F is a machine that processes x in a certain way to produce f of x. This is like a function that you might import into a computer program. You don't know necessarily what's going on in the middle, but you give it a function, give it an input, the function gives you a result. Same principle. The squaring function from R to R, defined by the formula f of x equals x squared for every real number x. Okay, this means that no matter what real number is inputted into it, the output will be the square of that number. Written symbolically as f colon x arrow, right arrow to x squared. The successor function, also known as increment, for integers, is g of n equals n plus 1. Just add to it. Since the z is an infinite set, you can always add 1 to it. So it is a function. A constant function is a function that yields the same result regardless of the input. That is the type of function that would return a void type in C++. It returns this. It does return a value. It's just value is nothing. It returns the same value, nothing, every time it's called. So that is a constant function. And they have these cute little pictures of functions and function machines and putting input in and getting output out, and what happens in the middle, you may or may not know. A function is an entity in its own right. It can be thought of as a certain relationship between sets or as an input-output machine that operates according to a certain rule. This is why a function is generally denoted by a single symbol or a string of symbols such as f, g, or log, or sine. Like I pointed out earlier, a relation is a subset of a Cartesian product, and a function is a special kind of relation. Specifically, if f and g are functions from set A to set B, and those two conditions are true, it follows that f equals g if and only if f yields the same answer as g given an input x. So, as an example, define the functions f and g from R to R by the following formulas. F of x equals the absolute value of x. G of x equals the properly positive square root of x squared for each x that is an element of R. Does f equal g? Yeah, because the absolute value of any real number is the same as the square root of its square for all x equals, or x is the element of R. All right.
So in the case for every element, for every real number, I mean, f will be.
F would be equal to g in that case, yes. Yeah, for all real numbers.
But if you're taking the square root of x squared, what would be also?
Like I said, properly, the positive square root of x squared is equal to the absolute value of that value. So, anyway, continue on the homework. I don't recommend getting ahead on the homework. You're only able to do one submission on the homework, so I suggest waiting until after the lectures on those sections to do those homework assignments. We're going to finish up chapter 1 on Tuesday. Thursday, beginning of class, we'll have a quiz on chapter 1. So have your notes ready and print it out. If you take notes on a tablet or your computer, print your notes out. And be ready on Thursday afternoon. Have a wonderful day.